Welcome to Notebook 24, Parallel Chains. This is the final notebook of Section 2. In this notebook, you're going to learn how to create and use parallel chains. And by the time you complete this notebook, you'll be able to create and use chains that have some component of parallel execution. And you'll be able to think about and identify opportunities for parallelism in your chains. Finally, there's going to be a mini project at the end of this notebook where you're going to revisit the mini project you did in section 1. However, you'll be leveraging your ability to create LangChain chains to accomplish this task. And furthermore, you're going to identify opportunities for parallelism in this task and implement a LangChain chain that is able to do the work in parallel where possible. It's worth mentioning, as we did when we introduced batching, that large language models have a lot of parameters. They're running on GPUs, which have a certain amount of GPU memory, and it's often the case when we're sending a single prompt to a large language model that the model itself and the GPU resources backing the model are underutilized, right? We're only using a fraction of the amount of compute that we could be doing at a given point in time. So if you're using a large language model for a one-off task or for a task that you don't do very often, then sometimes you may not be terribly concerned about the performance of your code. And you may even find that you intentionally choose to forego both the required thinking and coding effort that goes into making your code run in parallel because the time spent isn't worth it for something that you're only going to do every once in a while. However, if you find yourself writing applications that are being used heavily or extensively or are in some way on the critical path or are at some kind of scale where it could make a difference, then knowing when and how to utilize the resources at your disposal more effectively can, especially over the long term, really add up both to better performance and also for savings, right? If you have a limited amount of compute at your disposal. So doing the kind of formal analysis to ascertain when exactly that's necessary is both something that's specific to the use case that you're going to be working on, but is also kind of outside the scope of this particular course. So we're going to focus here on how you can do it, but I want you to all be aware that, again, as you move from the territory of kind of one-off, barely run, or not very often run tasks into the territory of language-related tasks that are running frequently or constantly or at high volumes, right? As you move into that territory, it really can be beneficial for you and your organization to think about where you can both do things in batch, which exposes a form of parallelization, and also use the techniques we're going to explore in this notebook for parallel execution within the context of LangChain chains. We'll begin by making our imports. We have one new import in this notebook that we haven't seen yet. It's part of the LangChain core runnables, and in addition to runnable lambda, we're going to import runnable parallel. We'll be using that below. We'll create a LLM instance using Chat NVIDIA as we've done throughout the course. Okay, so let's talk about parallel chain execution. We're going to look at a toy example to help get your minds kind of thinking about parallel execution and to explore the syntax. And then we'll be coming back later to actual large language model related tasks where we'll utilize parallel execution. Excuse me. So for the previous set of exercises, you composed multiple chains to operate on a set of inputs serially, which is to say in a given order. And as a matter of fact, if you remember our tasks from the previous notebook where we did grammar and spell checking and then generated a paragraph, we needed to perform the spell and grammar checking before generating the additional text, right? There was a dependency from the first into the second At times, when thinking about a chain of tasks we wish to perform, we might ascertain that some of the tasks can be performed in parallel. And the great news is that LangChain expression language provides us with easy to use syntax for the parallel execution of runnables in our chains. So we're going to begin our study of parallel chain execution with a non-LLM related set of tasks, just to get familiar with the syntax. And then as stated, after that, we'll apply what we've learned to create a chain that utilizes multiple LLM chains working in parallel. Okay, so first we need to identify opportunities for parallel execution. It may seem obvious, but before we can actually perform parallel execution, we need to identify when it's possible. You might, depending on your background, already be well practiced thinking about the possibility of parallel execution from work you've done in other programming settings. For example, if you've worked directly with CUDA code, there's other programming paradigms as well. Maybe you're already in the habit of thinking about when code can be executed in parallel. But if you haven't ever done that before, we hope you'll find that with a little practice, it's a skill that you can pick up sufficiently pretty quickly. In general, you just need to consider when the output of one process is required as input to another. In such a case, if it is the case that the output of one process is needed to be complete as input to the next process, then you've likely discovered the need for serial execution between the two processes. If, however, both or many of these processes can operate without relying on the work of other processes, then you likely have an opportunity to do parallel work. Okay, so let's explore this with a toy example. All right, and this is totally like kind of a silly example, but by keeping the example silly, we can focus on thinking about parallel execution. So we're going to define this text variable. It's the title of this course, Building Large Language Models with Prompt Engineering. And again, for the sake of exploring this theme, let's say there's two things we would like to do with this text. One, we would like to have a title-cased version of the text. And two, we would like to have a count of the number of words that the text contains. Okay, so let's ask ourselves, like we just suggested above, does the output to either one of these inputs is the output to either one of these inputs needed in order for the other process to be done? And looking at this, we can ascertain quickly that the answer is no, right? We don't need to title case it before we count the words. And also, we don't need to count the words in order to do the title casing. They're independent. So therefore, right, these tasks can be performed independently. And because they can be performed independently, we should be able to execute them in parallel. Okay, so let's look at that in the context of LangChain. To begin, we're going to create two runnables using runnable lambda, and each one is going to capture one of the subtasks that we wish to perform. So first we'll define a runnable using runnable lambda that allows us to do title casing. It's a simple lambda function that takes text as input and returns the title cased version of that text. Next, we'll create another runnable lambda called count words that takes text as input, splits the text on words, and gives us the length of the list of split words, thereby getting the word count. So, just as a sanity check, we can invoke both runnables with our text sample and make sure they behave as expected. So here we're going to use our title case and we're going to invoke it with text. You can see we get our title case back. Here we're going to invoke our count words runnable lambda with text, and you can see we get the word count back, which is 7. So if, right, going back to the pre-parallel world, if we wanted to create a chain to execute these two steps serially, we could pipe them together. Though, of course, we would need to take some care about the order of the serial pipe, right? So let's create a chain called serial chain where we title case it and then count the words. We can invoke that, and we can see we get the 7 back, which is the word count. Now, of course, when we're doing serial execution, we have to take care about the order of operations. If we reverse this, then it wouldn't work at all. And furthermore, it's just worth pointing out that our goal is to have both of these things, and at this point in time, our serial chain only gives us the output of the second. Okay, so we've seen that we have 2 bits of functionality. We've reviewed how we can combine them into a chain in serial execution. But in order to create a parallel chain in LCAL, we can use runnable parallel. And the way runnable parallel works is that it expects an input dictionary where each property is going to be one of the runnables that we would like to execute in parallel. As with any Python dictionary, ours needs to contain key value pairs. In the case of parallel chain execution, the key is an arbitrary value that we're going to decide upon, and the value is going to be the runnable itself that we want executed. The parallel chain is going to return a dictionary with the same properties we specified, and the keys are going to be mapped to the results of the runnables that we passed in. All right, so that's a lot. I think an example is going to clarify. So here we're going to create a parallel chain variable. We're going to do that by invoking runnable parallel. And as mentioned, runnable parallel is going to expect a Python dictionary. We're going to define a dictionary with 2 keys. One is going to be title, one is going to be word count. And for the title key, we're going to provide the title case runnable. For the word count key, we're going to provide the count words runnable. We're now going to define that parallel chain. Next, if we invoke that chain with our text, which if you remember is the lowercase version of the course title, you can see that the parallel chain returns a dictionary. It has the same keys that we specified here, title and word count, but title has been mapped to the result of the title case runnable being passed in the text that we invoked it with. And the word count key, it has been mapped to the result of invoking the count words runnable with text. And there's no real way for you to see it at a low level, like what happened under the hoods, but it's not the case that it did this one thing and then this second thing. In fact, under the hood, LangChain took care to do each of these in parallel and return the results as quickly as possible without waiting for one to complete before doing the other. Just to kind of explore this further and to help build up your intuition, if you recall, we have this getGraph method, and let's print it out for our parallel chain. And you can see that this kind of simple visualization kind of clarifies what we've been discussing here in words, which is namely, we have a parallel chain that is going to provide us with 2 values, a title and a word count. And just, this simple ASCII drawing kind of shows that these 2 forks, right, these 2